Hello, welcome back. We are beginning our week 6 lesson. That will be on electromagnetic wave. The previous lessons on the AC circuit, the behavior of the LC oscillator will help you appreciate better how Heinrich Hertz discovered the existence of electromagnetic waves. You can read about that in this handout. In this first part of 2 videos that I'm going to give, I'm going to explain to you how Maxwell was able to predict the existence of electromagnetic waves, how he was able to tell that light was also part of electromagnetic waves, and how he was able to tell or predict the speed of electromagnetic waves. All this he did and even passed on before the discovery of the existence of electromagnetic waves. Earlier on, we've seen how he came to discover the existence of displacement current. We will see how that one became a stepstone to come out with these predictions. Let's start by reviewing parts of the Maxwell's equations. You can read about this in page 11. They are nicely explained there. In this activity, you can write the equation and then express the equation in words. That will help you appreciate the equation better. So for equation 1, equation 2, these are the Gauss law. One for electric field, the other one for the magnetic field. Our main focus will be on the last 2 equations. That's the Faraday's law and then Ampere's law, which was modified later by Maxwell. All right. So here we are, the last 2 laws, the third law, which is Faraday's law, and then Ampere's law. In this first video, we are going to see another way of writing this third law, another way of writing it. Then in the next video, we will see another way of writing this one, the fourth law, and then we combine them to arrive at what we mean by electromagnetic waves. Let's begin with this 3-dimensional diagram. The axes are in space, but I'm going to add another axis. So I'm going to add another axis. That will be the electric field and the magnetic field axis with space. So this side will be the magnetic field axis. This side will be the electric field axis. Yeah. Then this side will be a 1-dimensional distance. That's x. That will be in the x direction. Okay. So we assume an electric field varying with distance. Let's draw something like this, a curve that is varying with distance. I mean, any curve at all. Then we take a closed loop, said that the x direction is so small, so we have dx. And then we take 2 points along the curve. That's a point where we have the electric field to be E, and another point here where we have the electric field to be E plus a small change. So from this point to this point, the electric field has changed from here to somewhere here. Because we want to explain to you, we've made it significantly big enough, but we are talking about a very small distance in which the change in the electric field will be very, very, very small. So differential, it's a differential. So this side of this loop is electric field E, and this side of it has an additional factor or additional term, small change in E. So that's it. So E, electric field, is changing with distance along the x-axis. All right. From the second law, Faraday's law, what we are saying here is that the line integral of the electric field will give us the induced EMF. Remember this one. This time around, we are not having the number of turns because we are only talking about a single loop like this, a single loop caused by change in electric field. So we are now not talking about the number of turns, because this uh, electric field is not due to the flow of current. So we are no longer talking about a solenoid with n turns. No. So let's see another way of writing this integral. What this one means is that we are going to multiply the electric field by the line, the various portions of the path, four sides of a rectangle. Okay, so for each side, we are going to multiply the corresponding electric field along that line. Then we sum everything together. So that's what we've done here. The left-hand side of the third equation, that Faraday's law, is given as this one. And what it means is that multiply all the individual length of the loop by the corresponding electric field. I've added additional line to make what I'm doing here much simpler. So what I'm saying is that we are moving in this direction. We are doing the line integral along this direction. In that case, this side is positive and this side will be negative. So this is what we do. We have E plus dE multiplied by H. So this side multiplied by the length, which is H. The electric field along this line is E plus dE. That's what we've multiplied here. Okay. Plus electric field times dx. There is dx, small dx, but the electric field along the x-axis at this side is 0. There is no horizontal component of the electric field. So that will be 0. 0 multiplied by dx. This one represents the L, the length of the line integral. Then we come here. We are moving, I told you we are moving in this direction. So if we are moving in this direction, then we are talking about the negative, the reverse of the electric field here. That will give us negative E times the length, which is H. Okay, so negative E times H. Then the last part of the rectangle, which is this side, it has a length of dx, small change in x. And then we multiply by the component of E in the x-axis. I told you, as we did here, it was 0. So it is 0 here also. So it is 0 dot dx. That's what we have here. So I've explained how we got each term in this long expression. I've told you this side is for this multiplied by the length, which is h. Okay, then this side is the x multiplied by the horizontal component of x, of the electric field. There is no electric field along the x-axis, so it is 0. 0 dot dx. Then we come to this side. That will be the negative of the field. The field is shown in this direction, but we want the opposite direction because we are moving in this direction. We are integrating along this direction. So we take it, the negative aspect of E multiplied by the length, which is H. Then finally, we have this side, which is dx, but there is no electric component along this side. So the electric component is 0 multiplied by dx. We simplify the whole thing to get this side, which is E dx times H minus EH. And eventually we get something like HDE. Because if we expand this, then EH will be taken care of by another EH here. So it will be left with DEH or HDE. That's it. That's what we get eventually. Okay. Now let's take the right hand side of the equation also and see how we can express it. The right side of the equation says the rate of change of the flux gives us the induced EMF. Now, flux is given by magnetic flux. So B dot A. I hope you remember. Dot here. Let me indicate magnetic flux. Okay, so magnetic flux is B dot A dot product. All right, in that case we should have vectors here. Okay, so if we have d phi, then we can write dB dA. So that's what we've written here. The dt remains there. So if we write it this way, then we can also express the dA in terms of h dx. If we have a rectangle with a side of h and the small side being dx, then the area is simply h times dx. So the small area here is h times dx. Alright, so it's h times dx. I think we can cancel this d here. We can take away this d. Alright, so h times dx. That's what we get for this side. What it means is that the whole of this right hand side can be expressed this way. So here we are. We have this side of the equation, this side being the same as this, and then this side being the same as this. So we can now bring this side together with this side. That's what we've done here. So that HDE now becomes equal to negative dB dt h dx. We can take care of the h, can take away the h, and we have dE negative dB dt, then dx. Then we divide through by dx so that the x becomes a denominator under this one. Okay, so this is a very simple equation. We are making it differential because we are now differentiating with respect to two different variables, x and then t. So the differential of the electric field with respect to the distance x is equal to the negative rate of change of the magnetic field with time. You see, so the field is changing with distance will induce a rate of change in the magnetic field with time. Okay, so this, the first part of Maxwell's steps towards predicting that there exist an electromagnetic waves. We'll come back with the second video to see how he used the fourth equation, how he used the fourth equation to also merge with this one in order to predict